Okay, so today I'm going to talk about the first lab for microprocessors. So this is the lab that we'll be doing that sort of incorporates a couple of things. First off, it talks about um, using the microcontroller to uh, do some, turning off of lights and LEDs. I mean LEDs and using the joystick to do different things from that board. So let's talk about that. So we're going to look at the GPIO basics, in particular in C, and what we need to do to accomplish that. Okay, so this is just a discussion about talking about Arduino boards, and I believe maybe y'all used an Arduino in your tools and toys class the year before. That's a little bit easier to use because a lot of the code is self-baked for you and you're not having to do a whole lot as you go through that course. And this just shows, what you might do when you're trying to hook up an LED. From a port that is a pin on the Arduino, you might run that pin which produced a high voltage out through a resistor and then through an LED and turn it on. Okay, so this is the example Arduino code that you would use. And so you can see that, okay, we're putting a digital pin high, waiting some length of time so it turns on and we see it. Then we turn it off and then we delay more time. And if we put that in a loop, then we're going to see the light turning on, off, and so forth. So this is just the simple LED turn on and off for Arduino. But let's see how we would accomplish that using our microcontroller in this lab. So it says here some of the differences from what you used before would be this Arduino offers higher level functions that hide all the low level code necessary to accomplish something as simple as turning on a single output line or high or low. That's not going to be quite so easy here. And so notice what it's sort of saying is this setup right here that just said, let's do some pin mode for setting up an LED and set it up as output. How are we going to actually do that on the ARM microcontroller? So we already talked about needing to do some things on the Cortex microcontroller to set things up. And so what are the similar commands? Well, they're right here. Now this is a whole lot more complicated, but again you'll see that it's basically just doing stuff that we already talked about. Okay, let's try to sort of look at it real carefully. You can see we're doing the reset and clock control register here, which we talked about, and we're going to turn the clock on. This is that exclusive OR operator. And so what we expect is that in all of this, okay, somewhere we've defined this, somewhere we've defined this. Again, that's the configuration register for the clock. All of these things have been defined somewhere, and where that somewhere is the startup files. So we've got these equate directives in the startup files that will allow us to use these nice names and so forth. Now, of course, this thing where we turn this is the high-speed clock that we're turning on right here. That's something that's going to have to be done in pretty much every code that we do. Then we have to wait for that clock. After we start, we have to wait until it's ready. And so what this is doing right here is it's saying, okay, while basically it's not ready, keep waiting. Once it is ready, then it will go to the next line here, and we're going to configure something there, and then we're going to configure something here. And again, these aren't really things that we have to know about, but just realize that that's what it's going to do, is it's going to configure this clock that we've got. And so basically it's going to configure the clock speed of what we're trying to do right here. Okay, so we were talking about the different equate directives in a previous chapter about the ARM, I think arithmetic, logic, options, operands and so forth. So these are all equate directives: the high-speed interface on, high-speed interface ready, configuring the switches, blah, blah, blah. Now the one that we've sort of been aware of is this is the high performance bus to enable, and here we're doing the GPIO and port A enable. Now one thing you might remember, so in there we have, in the startup files, we have a bit sequence, and what we know is that that bit sequence is encoded for this right here to turn the GPIO port A on. You see that it's exclusive ORed here, so we talked about that. So what you're basically doing is you're saying, I'm going to exclusive OR the enable register with what would enable the GPIO port A. Then, okay, the other two things we have are these two. And we've talked about the motor register before. And so you can see here we're doing something with exclusive ORing with a 1, and then ANDing with something that complements and has all zeros and a 1, so it's going to be all 1s and a 0 then. So we're doing something like clearing, it looks like, that first bit. Well, we'll see what we're going to do later on in the code just to make for sure, but the essence of this is all of this code over here is done in this little pin mode function that is in the Arduino code. So anyways, this is sort of telling us a little bit about what we have to do, and how we have to configure all the registers manually. Okay, so here's just a sort of generic idea of what's going on with the GPIO ports. It's just a pin that is on an integrated circuit in the microcontroller, and it is able to be either an input pin or an output pin, and we get to configure that at runtime. We can enable and disable the pins. You can see we can read them as highs or lows from inputs. Output values are writable or readable. They can be used as interrupts for wake-up events. We also can have analog as a function for our input outputs. Okay, so we have the 32L4 discovery board, which is an M4 board, and you can see what this is trying to tell you is that we have headers along one side of the board and headers along the other side of the board. We have the joystick, which we can control. We have like a couple. Okay, so we have the header pins on both sides of our board. We have the green and red pins that are accessible and tied actually to the ARM chip. We also have the joystick and center button that is tied to the chip. You can see that just the ARM controller by itself has GPIO ports A, B, C, D, E, and F. Now, you don't have access to all of those pins from those ports on the discovery board. Lots of them go out to these spots here and here, but not all of them. Some of those ports are attached to here and other spots as well, but you don't have all of the ports accessible via the headers. But you do have access to the code, or from code, to all the GPIO ports through software. You just may not be able to access the port unless you go hook up to the pin on the controller itself. Okay, so the first step when you're using the GPIO ports is you have to identify which ports you're going to use, and you have to activate the clock form. So this tells you in more detail what those first steps have talked about. We're going to enable the high-speed internal clock. So that's what this is doing right here. We're going to turn it on. Okay, we're going to wait until it's ready and running. So that's this while. And so that's just sitting there waiting until it gets that it is ready. Once it is ready, then when it returns this and it matches the ready construct, then it's going to exit out of the while loop so that we are ready. And then, okay, now we're going to use the configuration of the GPIO port, and we're going to use the software configuration of the high-speed internal clock to be used as the system clock. So that's what's going on right here. Again, not something that we'll have to actually use too much, except, or maybe I should say, not something we're going to have to know too much, but just it has to be there. We have to have that high-speed clock used as the system clock. That's what's accomplished there. And then we're going to wait until that's finished being done. So this is, you'll see this at the top of the code that you've been given. What you have is in this lab, you'll have a template code that you can download from Blackboard. You'll see it for Lab 1, Lab 2, Lab 3, Lab 4, Lab 5, but you download the template and then you should be able to modify the template to be able to do the different things that you were requested to do in the lab. Okay, so the main thing that's going on here is now, in addition to just setting up the high-speed internal clock and then using that as the system clock, we have to configure the GPIO ports. Okay, here's where we're going to enable, notice this is the same, and each time we're exclusive ORing that with a bit pattern, a bit mask that will enable port A, port B, port C, and port D. That's what the enabling of the clocks is done by. So once you're done with that, the clocks are enabled, and then you can do modification of the ports themselves. We talked about doing the inputs, outputs, push-pull, all that sort of configuration. But this page right here follows the process that we have to go through to set up and enable the GPIO ports. Okay, now each GPIO port, we already talked about this, they have all of these registers associated with them. The port, the motor register, the output type register, the output speed register, the pull up pull down register. All of these are these important registers that each GPIO port has, and then we also can see there's an offset for each one of those registers. And so once we know the base address of the specific GPIO port, then we can use the offset address, which will tell us about where the different registers are within the GPIO port base address, so how far away they are from that base address. Okay, so the next thing we have to do for us is we're going to try to talk about the motor register, and specifically how would we need to set up each pin that we're trying to do. So it shows you here, okay, the motor register for GPIO-A. Remember, we could calculate or get the membership operator like this, so we can get the motor register for port A, and we can set or reset bits that will control each pin. So there's 32 bits, and the motor register, remember, all of these registers are 32 bits except for this one, which is a 64-bit register, and it has 32 bits high and 32 bits low to create that 64-bit register. And remember, the key for the GPIO ports are that we want to do, for this motor register, we can set it as a input, an output, alternative function, that's what we talked about as AF previously, or analog. Okay, now, if we look at this one right here, it says GPIO-A motor, exclusive or equal, and then we have this 3 stuff here. So what we're doing, 3, remember, is basically going 0, 0, 1, 1 with those last bits. So I'm exclusive ORing a bunch of zeros and then 0, 0, 0, 0, 0, 1, 1. So what that's going to do is it's going to set these last 2 bits as 1. Now you might say, okay, well, that's setting that as analog. Did I really want to do that? Well, no. Then remember, you see the next case, we're doing and we're doing, so the mask operator is the same for both of these. It's this 3. So if we do this mask operator here, we can see we're going to take the 3 again, so 0, 0, 1, 1, but then we're going to use the complementation part, so that's going to be 1, 1, 0, 0, and then we're going to AND the motor register with that. So what that's going to do is there's going to be 1s everywhere except these 2 bits right here, and so that's going to put a 0, 0, and so that means this one is going to be set for digital input. So specifically what we've done is set port A 0 for digital input here. Okay, we can also set the output type if we're doing output here, and then you can see, in addition to that, we can set the pull up, pull down register. So we've talked about these a little bit, but we have, if it's an output, we can set up push pull or open drain, and of course we expect most of the time we want push pull unless we're going to supply our own source and pull up from that there. So we're going to likely use that for the push pull output style. And then the other thing is we have no pull up, pull down, pull up, pull down for the pull up, pull down register. And notice that this one is 2 bits for each port. So if you were doing port A, you got to do bit 0 and bit 1 within that pull up, pull down register. What do we want to do if we want to read or write a value from the port or to the port. We're going to read from the port. We need to read the data into the input data register. If we're going to write something out to the port, we're going to write to the output data register. So you can see for each port we're going to have those things. Since they're 16 bits, then we just have the 16 bits right here. And for our port inputs, for the input data register, we're going to we can do something like that. If we want to set something on the output data register, it's going to look similar, except it's going to be ODR rather than IDR. Okay, so let's just see what these two commands do if we were to implement them. It says this is going to set bit 2 of GPIO A port to 1. Well, notice what we're doing is you see 4 here, so the last 4 bits are 0, 1, 0, 0. That's 4. All the rest are 4s. So, excuse me, all the rest are 0s. So we have this going in. That is setting bit 2 as a 1. So that's right there for that GPIO A port. And so what that's doing also is it's saying, okay, we're going to exclusive OR by sending this out. So we're going to send 1 on port A2. That's what we're doing with that particular command. Now notice we're exclusive ORing. So what are we doing with all the other bits? Even including these three right there, we're not affecting them. We're not doing anything to them because ORing with a 0 does not change anything, as does exclusive ORing with a 0. They're left at whatever they were. Now, what about this one though? This one is checking bit 2, it says, and let's just see. This is looking at the input data register and saying, okay, this is looking at the input register for GPIO port, and it says, okay, we're going to AND it with 4. And so what this is saying is, okay, what is 4? 4 is, again, 0, 1, 0, 0. And we're going to AND that with whatever we have in the input register. Well, if we AND that, and this bit is a high, and that port 2 bit is also a high, then what happens? We get a true out of that. And if that's true, then we can execute code based on that. If it's false, then that means it's a 0, and we can execute code based on that. So that's how we would check those bits. Okay, so let's look at the bit set and reset register of the GPIO ports. What this allows us to do is set individual or a combination of lines, or reset a individual or combination of lines using a register. So that means we don't have to do the complicated output formatting that we might sometimes feel like we need to. Okay, so how this works is we have 16 bits that are the lower 16 bits, sometimes referred to BSRRL, so the lower 16 bits of the 32-bit register. And if we want to set line 0 through line 15 as a 1, then we'll put a 1 in that particular bit. So if we want to set bit 0 to a 1, then we'll put 1 in that register. What if we wanted to set bit 1? What would we put in that register? We would put in a 2, right? Because 2 would be 0010, so it would get bit 1 of the port and set that to a 1 at the output. So just to make sure it's clear, what would happen if we put, let's say we crossed off this 1 and we put A, because this is hex, we can put A, which is 10, right? What is 10? Well, 10 would be 1 0 1 0. What does that mean would happen? That means bit 1 on the port would output a 1, and bit 3 would output a 1. So you can do multiple bits if you want to, but that's, how you would do multiple bits. Okay, so that's if you want to set that line or that bit on the port to a 1. If you want to reset the bit, you have two possibilities. Okay, you can use the upper 4 bits in the BSRR register, and if you set those, you can think of them as, even though they're bits 16 through 32, they're really resetting the lines 0 through 15. So for example, if you put the A here, what that's going to do is it's going to reset those outputs for bit 1 and bit 3. So putting a 1 in the lower 2 bytes of BSRR will set the pin that you want to output as a 1. If you put a 1 in BSRRH, the upper 2 bytes, that will reset that line or put a 0 out on the output of that line. Now, one thing you can't do is you can't do something like, for example, you can't do BSRR, you can't do something like 0001, 0001, because that tells it you want a 1 on the bit 0 output from setting it, but it also tells it you want a 0 on the output for resetting it. So that is not valid to put out on the BSRR register. You can't have that complementary set and reset at the same time. BRR is only 16 bits, and basically BRR is the same as BSRR, except you're resetting for those lower bits rather than setting for those lower bits. So it doesn't really matter. I think you could do it either way, but in our experiment that you'll see later, we actually show using BRR. So let's talk about that slide a little bit. Okay, so now how are we going to handle the joystick? The joystick needs to be configured as an input, and the pull-up, pull-down register needs to be configured for pull-down, because we need to be able to pull these inputs down. We don't have those resistors there in the first place. We do have the pull-up right there. This one actually does have the pull-down resistor, so we could get away without doing it for that one. But we need to do 1 0 for pull-down, and so let's look and examine what these registers are, what these operations are actually doing. We see that this is the AND bitwise AND operation, so we see that complement there. So let's see what CFF does. CFF, what it does is it gives us 1 1 1 1 1 1 1 1, and then C is going to be 1 1 C is 1100, because D would be 1101, E would be 1110, and F would be 1111. So that is the number 12. So when we complement that, what's going to happen, because we have to complement it right there. So now all the other bits are zeros there. So when we complement it, we're going to end up with 1111 for each one of these zeros, and then this 0. So we have 1111, 1111, 1111, 1111, 1111. So then we have this complemented, and it's going to be 0011, and then 8 zeros. So when we end with that, what that's going to do is give us zeros in those lower 8 bits, and then those 2 bits right there. Well, what is that going to do? Well, we need to do something with port A0, 1, 2, 3, and 5. So we're skipping needing to do something with port A4. Hey, that's where those 2 bits are doing something. So we're clearing those bits, and let's make sure we see that if we go way back to the pull up, pull down register. There we are. You can see, okay, putting 10 for pull down in these 2 bits, these 2 bits, these 2 bits, these 2 bits. We're skipping these 2 bits and we're putting them in those 2 bits. So that sets up 1, 0, 1, 2, 3, and 5 for port A in our particular setup right here. Then what are we doing? We're putting in 0000 08A, and we're doing the bitwise OR operation for that. So what is that? That is 1010 is A is 10, so 1010 is 10, 1010, and then 8 is 0100. So you can see what we're doing is we're setting the pins that we need to set to do the 10 or pull down. So there's pull down for A0, pull down for A1, pull down for A2, pull down for A3, not messing with A4, pull down for A5. So we've set all the ports for pull up we've set all the ports that we need to for pull down for our setup here. Okay, so let's then look at the code and see how, if when we press up on the joystick, can we get that to turn on the green LED? So let's go back and just make sure we understand, hey, what's up? Going here, up is 4. 4 is right there, so that is going to port A3. So port A3 is the one we need to look at, and that's indeed what you see right here. It's saying, okay, let's compare the input data register to what is on a 1 in that particular location. So this is saying an unsigned integer, value of 1, left shifted 3. So here, if we shift it 1, we'll have it that way. Shift it again, have it that way. Shift it one more time, and we'll have it that way. So we're going to have a 1 in pin 3 right there. So it's easy to tell which pin you're looking at by just shifting that many times. So this is going to AND, so it's going to AND the input data register with a 1 in that location. If we have a 1 in that location, then that'll be true. If it's not, then that'll be false. And so it says if it's true, then that's not equal to 0, and we'll go into this spot. So if this is true, we're going to go in here. And what happens? Okay, here's this bit set and reset register. What's it doing? Oh, we're moving 1 over 8 times. So that like this, that's going to do something with pin 8 and port E. Oh, that's port E. So we're putting port E8 and we're putting that to a 1, right? Because that's the bit set reset register and it's in the lower part. So we're setting that bit to 1. Oh, that should turn on the green LED. That's what we're doing right here. Then we say else if it's not pressed. So basically this is saying right here is if pressed, then do this stuff, else not pressed, turn the light back off. Because that's what this is doing. It's doing with BRR, it's resetting that line to 0. If we don't reset it, it's going to stay on once we turn it on. It won't turn it back off. So this has to be done to reset the output of that line. Of course, we could have done BSRR equal 1U left 8 plus 16 to do it in the upper part, because that would be a reset then as well. Okay, so then this particular set of code tells us how to do that. Light up the green LED when the up button is pressed. There's more than one option, and that's what this is trying to show here, and I'll let you all go through it with a little bit more detail for yourself. But here it's trying to say, okay, what happens if we press up? When we press up, okay, we can do exactly what we did before. And what does that mean? We can set port E8, so that's going to turn on the green LED. Well, what's this one doing? This is B2, right? Because we're shifting 2 and we're on port B. Oh, we're turning that off. Looks like by the BRR instruction, not instruction, by the BRR register. What is going on here? So that's pressing up, turning on this one, turning off that one. What is this one doing down here? If port A and this looks like it's doing shifting twice, so this is 2. So it's saying if that's pressed, okay, we're doing BSRR for B2. So we're going to turn on that LED, we're going to turn off the other one. So we're basically flipping which way they are. Well, what is this? What is GPIO port PA2? Let's see. PA2. Oh, that's the center button. So that's what would be there. So anyways, that gives us the option of what's going on there. Let's look at one more option of actually generating these different if-else kind of statements, and that is with the switch statement. And let's look at what's going on here with a switch statement. Oops. Okay, so let's look at one more option to have like an if then else statement if we want to turn on LEDs or whatever based on joystick ports being pushed. So whether or not up, down, left, or right is being pushed. So let's look at this and see how we could do it also with the switch statement. And so what we're trying to do here is generate the types of things that might happen with the switch statement. Okay, so we're basically saying we're going to do a bitwise AND of the input data register and 2F. Okay, well 2F is basically going to give us 1 1 1 1 and 0 0 1 0. So this is the last 8 bits, and then of course we have 0 0 0 0 0 0 0 0. So if we look at the 16-bit number, of course it's 32, and we could continue that on out with zeros if we wanted. But basically you see we're looking at taking the input data register, which is basically IDR is going to be PA0, PA1, PA2, PA3, PA4, PA5, ... So basically by putting these ones in these positions and ANDing, we're basically singling out PA5. Everything else is going to be zeros. P0, PA3, PA2, PA1, and PA0. And then we're doing case statements based on what the number is that we get out. So if we get, okay, no shift, in other words, the case is just 1, then that's if this one has been pressed. And then it would execute whatever's in here, and then it'd break to the end of the case statement. Of course, there is a default case that you could have that's not listed in here, but that would just be default before the end, and you could put that in. Case 1 shifted 1, so that's basically saying this one is pressed. And so forth. So you select which one it's going, and if you don't have the break statement, it can continue on and go through down there to the next case and not break out to the end of the curly brace there. But you can see the idea here would be to do this consecutively. Now, of course, you could have the case, let's say you could manage to do diagonally where 2 of the joystick buttons were pressed. Well, you could have that case where it's you know, that particular thing directly, say PA2, you know, say it could be let's say 0x or 0b, I'll just say 101, so the binary number 101, and in that case, if you had those 2 pressed, you would draw and it would go to that part of the case statement. So anyways, this is just an option, another option. You can do it with if, then, and else, but maybe this is a little bit more readable, and it's a similar situation where you can get it to execute certain amounts of code based on what is pressed. So anyways, it's just another option, and you can use the switch statement to also check which things to do.